Good evening, children. We were doing resonance. Today, let me give some example of resonance in organic compounds. First example that we do is C6H6. It's benzene, and the structure of benzene is this one. This is benzene. This is the bond line notation for benzene, bond line notation that we will be studying later on. Or let me write down benzene. Benzene has 6 carbon atom in a ring, and there is hydrogen with each carbon atom. And at alternate position there is a double bond. This is benzene, this one is same thing. So what happens is this pi bond shifts here, due to that this pi bond shifts here, due to that this pi bond shifts here. So another structure for benzene will be this one. So these two are resonating structure of benzene. This is not the structure of benzene. This is also not the structure of benzene. The actual benzene is the combination of both these structures. That we draw it like this. The resonance hybrid. So this is the resonance hybrid of benzene, and with the help of resonance we can explain this fact that carbon-carbon bond length in benzene are all same. Carbon-carbon bond length in benzene are all same. It is because we can say that benzene is actually this one. Benzene is a resonance hybrid of these two resonating structure, of these two contributing structure, or of these two canonical structure. So if you want to do it from here, same thing, it would be pi bond will shift here because of this one will shift here because of this one will shift. So this is resonance happening in benzene. Now one more example I will give from an organic compound, that is a compound called phenol. And phenol is represented like this. Phenol is represented like this. As you can, at each corner there is CH. At each corner there is CH. So in phenol, what happens? One of the H here is replaced by a OH group. If one H is replaced by OH, then it becomes phenol. And oxygen has a lone pair. So this is phenol, and now we are going to draw the resonating structure of phenol. So the first structure that we draw is this. What will happen is this lone pair will come here. Here there will be a double bond. Due to that, this pi bond will break and it will come over this carbon atom. So this will happen, and formal charge gives a minus sign here, because you see, if you calculate surrounding this carbon, there will be 5 electrons. How 5? 1 electron in this bond, 1 in this bond, 2 electron here as lone pair, so 4, and there is also a bond with H. There is a bond with H which is not being shown here. So that way there are 5 electrons surrounding carbon, 1 more, that's why it's minus here. And surrounding this oxygen atom, you see there are 5 electrons, 1, 2, 3, 4, 5, 1 less. So this oxygen is plus. So this is the first regularity structure we are getting, and subsequently what will happen is this one will come here, this pi bond will break, will come over here. Same way. Next, this 2 electron will form pi bond here. This one will break, will come over this carbon atom. And then this will come over here, will again go back here. So these are resonating structure or canonical structure for phenol. And you will see later on in class 12 many questions in organic chemistry, many problems in organic chemistry can only be explained through resonance. So resonance is very important in organic chemistry. So that you are doing little bit here in this chemical bonding. Okay, so after resonance, now let me take up another vital theory for covalent bonding, that is molecular orbital theory. We have discussed valence bond theory for covalent bond formation. We have another theory, that is molecular orbital theory. So, what is molecular orbital theory? It is suppose an atom A is combining with atom B to form a molecule AB, where the bond is formed between A and B. Now here we use a term called linear combination of atomic orbital linear combination of atomic orbitals. So what is that I am explaining it here. So this is energy is increasing, and suppose this is psi A, so wave function for an atomic orbital which is present in A atom, and psi B is a wave function for atomic orbital present in B atom. Simply we can say this is atomic orbital, this is another atomic orbital. This atomic orbital is present in A, this atomic orbital is present in B. And suppose each has got one electron. Now, according to linear combination of atomic orbitals, these two will combine to form two molecular orbitals. So, what is one molecular orbital? It is called sigma bonding molecular orbital, and another molecular orbital that is formed is sigma anti-bonding or sigma star anti-bonding molecular orbital. And this molecular orbital will be filled with electrons. So total there are 2 electrons, and according to Oppo principle, these 2 electrons will be present here. So this is what is a linear combination of atomic orbital. Atomic orbitals are present in atom. And in a molecule, actually, we have molecular orbitals. These are the molecular orbitals, and in electron in molecules are present in molecular orbitals. Now, here you have to know about different molecular orbitals. That is important. Now, I am showing you some molecular orbitals that results by combination of atomic orbitals. So this is our 1s orbital. This is also our 1s orbital. This is of one atom. This is of another atom. And when they combine, they form a molecular orbital which is called sigma 1s bonding. Now this has resulted by addition overlap. Addition overlap means this one is plus. The sign of wave function is also plus, and this one will be plus plus. and the sigma 1s bonding and subtraction overlap results in an anti-bonding molecular orbital. Where there is a nodal plane here, and this is sigma 1s anti-bonding molecular orbital. So 1s and 1s combines to form sigma 1s bonding and sigma 1s anti-bonding. This one has higher energy than this one. In this way we have sigma 2s bonding, sigma 2s anti-bonding. So 4 molecular orbitals we have come across till now. Let me write down them in increasing order of energy. Sigma 1s bonding, and then sigma 1s anti-bonding. Then if we consider 2s, it will be, you'll get sigma 2s bonding, then sigma 2s anti-bonding. Okay, now let me take up the case of 2px, sorry, 2p of this atom when combines with 2p of this atom, then what sort of molecular orbital will form? Now 2p, 2p consists of 2px, 2py and 2pz. So we have to think of combination of pz. We have to think of combination of py and px. Now one assumption which is considered in molecular orbital theory is internuclear axis. The line joining the two nucleus is considered to be the z-axis. That you have to remember. The internuclear axis is considered to be the z-axis. So I am showing you now first what molecular orbital results when 2pz combines with 2pz. So 2pz combining with 2pz, what results? Now this is 1 2pz. So this one is p orbital has one lobe plus, another lobe minus, and another 2pz of this. So this is plus, this is minus, this is also 2pz. So now these two combines and forms two molecular orbital, and one molecular orbital is called sigma 2pz bonding molecular orbital, and the other one is sigma 2pz anti-bonding molecular orbital. Now I am drawing now the shapes of this orbital. First this one. These are the two nucleus, and so this is minus, this is plus, this is also plus, this is minus. this is sigma q is a bonding molecular orbital. You will always see in bonding molecular orbital, in between the nucleus, there is more electron density. There is more electron density, and it is just opposite in case of anti-bonding molecular orbital. So this sigma q is an anti-bonding. How it is? It is like this. The two nucleus, and so this is now subtraction overlap. This is plus. So this is plus. Now it will be minus. Minus plus doing subtraction overlap, and due to that sign will change here. This plus has become minus, so this minus will become now plus, and similarly this one will be minus, and here there will be a nodal plane. So PZ combining to form sigma to present bonding, and sigma to present anti-bonding. As already said, here we have considered, according to convention, we take the internuclear axis as a z-axis. So we got another two molecular orbital. Now, what happens when, say, px and px combine? What happens when px and px combines? Okay, now if pz is this, certainly px will be perpendicular to this. So I am drawing the px now here. So this is our 2px. So this is plus, this is minus, the nucleus, and another 2px plus, minus. So LCO of linear combination of atomic orbital of these two will give us one is sigma 2px bonding molecular orbital, and another will be it won't be sigma here. Previously it was sigma. Now it will be of pi type. Pi 2px bonding, and another will be pi 2px anti-bonding. Why pi here? It is because here when they combine, they will combine laterally. They don't combine head-on. PZ had combined head-on. If PZ and PZ had combined head-on, PX and PX has to combine sidewise. So let me draw this molecular orbital now. This is one nucleus, another nucleus, okay, and so this is plus, and this one will be minus. This is our pi to px bonding molecular orbital, okay, and the anti-bonding one will be like this, which is subtraction overlap. This is plus, this is plus, this is minus, and the sign will change here. This is plus, it will be minus, this minus, it will be plus, and here there will be a nodal plane. So 2px and 2px combining forms pi 2px bonding molecular orbital and pi 2px star antibonding molecular orbital. Exactly this way only py and py combines. That I am not showing here. So, so these are the molecular orbitals that will be there, for molecules of second period. In your syllabus, you have only molecules of second period. You don't have beyond that. So, let me write down all the molecular orbitals that we have got so far according to their energy order. So, sigma 1 is bonding, sigma 1 is anti-bonding, sigma 2 is bonding, sigma 2 is anti-bonding, and after that it is sigma 2pz bonding, then it is pi 2px bonding equal to pi 2py bonding, then it is pi 2px antibonding equal to pi 2py antibonding, and the highest energy this molecular orbital possesses, that is sigma 2pz antibonding. So these are the different molecular orbitals, and in molecules of substance, we have these molecular orbitals, and electrons are present in these molecular orbitals. Just like in an atom, we have atomic orbitals, electrons are present in atomic orbitals, but in a molecule, say H2 molecule or O2 molecule or HCl molecule, for that matter any molecule, we have in a molecule molecular orbitals. These are the molecular orbitals, and electrons are present in these molecular orbitals. So now we will do molecular orbital treatment of some individual molecules. To begin with, let us do for hydrogen molecule, simplest molecule. So suppose hydrogen molecule, here we have a total of 2 electrons. So the 2 electrons will be coming here. The rules for filling up of electron in the molecular orbital is same as the rules for filling up of electron in atomic orbitals that we have studied in previous chapter. So in hydrogen molecule, 2 electrons will be present here. So its electronic configuration, this will be sigma 1 is bonding, 2 electron, and all these other molecular orbitals will be empty, no need to write down. And so this is over, and bond order is a term in molecular orbital theory which tells us about what type of bond is between the 2 atoms. And bond order definition is number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital and divided by 2. So we have 2 electrons in bonding, there is no electron in anti-bonding. So bond order we are getting 1. It means here the 2 atoms are connected by a single covalent. Now let us do for next say helium. Now you all know that Ag2 helium molecule does not exist. So why Ag2 does not exist, we can get explanation from molecular orbital theory. So let us begin with this hypothetical helium molecule. So here we have total of 4 electrons in hypothetical helium molecule. So its configuration will be sigma 1s bonding 2, then sigma 1s anti-bonding. The next high energy molecular orbital is this one, 2, no other molecular orbital. So bond order will be, there are 2 electrons in bonding minus 2 electrons in anti-bonding divided by 2, 0 by 2, 0. So bond order 0 means there is no bond. If there is no bond, that means this molecule does not exist. So we are getting explanation from molecular orbital theory that helium molecule does not exist. Now, one last case I will be giving you here is, say, oxygen molecule. Oxygen molecule, we know oxygen molecule according to valence bond theory. According to valence bond theory, it was like this. There is a double bond, 1 sigma, 1 pi. That is what we have got in valence bond theory. Let us see what we get in case of molecular orbital theory. Oxygen molecule will have in it how many electrons? 8 plus 8, 16 electrons. So we have to arrange these 16 electrons here. So the arrangement will be like first sigma 1 is bonding 2 electron, then sigma 1 is anti-bonding 2 electron, then next comes sigma 2s bonding 2 electron, next sigma 2s anti-bonding 2 electron, next sigma 2pz bonding 2 electron. So I have used how many? 2, 6, 8, 10. 10 electron I have already used. Another 6 to go. So now it will be filled up here. So this can hold a total of 4 electron. This 2 and this 2. So pi 2px bonding 2 electron is equal to pi 2py bonding 2 electron. So now we are left out with 2 electrons. So now that remaining 2 electrons, one will come here and one will come here according to Hund's rule or maximum multiplicity. One here, one here. So it will be pi 2px anti-bonding 1 equal to pi 2py anti-bonding 1. So this is the molecular orbital electronic configuration of O2 molecule, and now we have to calculate bond order. If you calculate bond order, so how much bond order comes here? Let us write down which are bonding electrons. This one, this one, this one, this one, this one. The bonding electrons, so 10 in number. So 10 minus anti-bonding electrons 2, 4, 4, 5, 6. 6 by 2. So 4 by 2, 2. So bond order 2 means, like in oxygen, there is a double covalent bond, as we have got in molecular orbital, in valence bond theory. So let us do this much. There are some more examples we will do in the next class. Until then, good night.